talk about chapter 4, which is linear equations and linear regression. Oh, so I wanted to say something about the hypothesis testing. I was looking at the work you guys did in class on Monday, and some people were saying they made a conclusion, do not reject, and they say, because there is no evidence of whatever, okay? And that's not really an accurate statement. So if we say we're doing the chi-square test, okay? We know our chi-square curve looks like this. Okay, and so suppose we find our critical value is here. So that critical value is based on some amount of significance. It's based on, we want to be certain to a degree that we're not going to make that type 1 error, that we're going to reject when we shouldn't have. Okay? So if it's 5%, if this is a 5% rejection area, what we want to say is we want to make sure that we're not wrong about rejecting. So at 5% of the time is all we'll allow to be wrong about rejecting. So if you get a test stat right here, say your chi-square test stat is here, then it's not that there's no evidence, okay? So it's just the further you get this way, the more evidence there is, okay? So the further you get this way, the more evidence there is to reject, okay? So when you don't reject, it doesn't mean there's no evidence of the alternative. It just means there's not enough for us to have a certain amount of certainty. Does that make sense? So when you don't reject, you don't say there's no evidence. You're saying at this significance level, there's not enough evidence. Okay? Does it make sense? So this is not, the critical value is only, it's not like we're sure that the null hypothesis is true, and then suddenly here, now we're going to reject the null hypothesis because it's not true. It's not like that. The evidence is on a scale, right? Evidence is on a scale, and we pick a significance level, and then we have a cutoff point. So the further you move this way with your test stat score, the more evidence there is, even over here, even in the non-reject region. The further you go this way, the more evidence there is towards the alternative hypothesis, and less for the null. It's just we have to pick somewhere, so we pick somewhere based on making a type 1 error, which is if it's 5%, then we only want to be wrong. If we reject, we only want to be wrong 5% of the time or less. So we find that critical value based on rejecting incorrectly 5% of the time, and that's our cutoff. And so over here, we say, okay, there's not enough evidence to reject the null, and over here we say, okay, there's enough evidence to reject the null such that we're only wrong 5% of the time. Okay? So I just wanted to point, because we've done that hypothesis testing on lots of stuff. That's kind of an important point. Okay, changing gears. Chapter 4, linear equations. So all kinds of relationships in the world end up having a linear relationship between the two quantities or two variables. Not all, okay, but many. Okay, so there's all kinds of relationships between two quantities. Some of them in the world turn out to be to form a linear type graph. So here's an example of years. So starting in 1910 up to, say, 1981, and then the record time in seconds to run a mile. So this is how many seconds it takes to run the mile, and this is years. And you can see that that data is looking like it follows a linear pattern. Okay? Similarly here, so this is the number of games rented from some business, and then the total cost for renting that number of games. Okay? Follows a linear pattern when you graph it. Okay? Here's time in days and height of the grass in meters. Height of the grass in meters, and so it follows a linear pattern. Okay, so in a linear relationship, you have what's called the independent variable, and normally we put that on the horizontal or x-axis. Okay, so in this case, the year is the independent variable. And that's also called the explanatory. Or what's the other one? The predictor. Okay, so the independent or the explanatory or the predictor. So in this case, that would be the year. And then that's our x. Okay, that's x. Okay, and then this is the dependent. Or response variable. Okay, and that's y. Okay, so in the video game example, the number of games rented, that's our x coordinate, that's the independent variable, or the explanatory, or the predictor variable. And then the total cost for that number of games rented is the dependent or response variable, which we use the variable y for that. Okay, so now there's kind of a difference between, so one of these is different than the others. So which one is a little bit different than the other two? So of course, this one goes down and these two go up. That's not what I'm talking about. But in terms of just overall, one of these is different. Which one? Yeah, this one, the video games, is different. How is it different than these two? Exactly right. So because the business is setting their price. They have a certain price scheme, and that price scheme is exactly linear, right? It's exactly linear. If you rent 15 games, your price is already determined to be, whatever, $45 or something like that, or $50. And so according to their price scheme, the data will always fall exactly on a straight line. Okay? But in these situations, we take data in the real world and we see that the trend is generally linear. It's generally linear, but not exactly, right? So not all the data points fall exactly on a line. But the idea here, from a statistical standpoint, is that we can take this data that generally, like this one, we can take this data that generally falls on a line, and we can come up with what's called a best fit line. And that best fit line will help us to predict what it would be for data we didn't have. For instance, we didn't get a data point for 6 days for the grass height, but we can use the line to say, oh, we can make an estimate of what the grass height would be in 6 days, even though we didn't have a data point, and we can use the line to do that. Okay. So that from a statistics standpoint, the idea is we take the data, if it generally falls in a straight pattern, we can make what's called a best fit line to help us predict or determine other values that we don't have. Okay? All right, so for a line, the linear equation b naught plus b1x. B naught is the y-intercept, and b1 is the slope. Okay, so what are the meanings of these? All right, so we want to So that's our y-intercept and our slope. But we want to, so yeah, having a name for it is important, but more important is that we know what those mean in a given situation. So let's go back and look at those graphs again. So we could write, say, the video game. So it's b0 plus b1x. So b0 is the y-intercept. So in terms of the graph, what does that mean? That means where this graph crosses the y-axis or intercepts the y-axis at 20. So what's the meaning in the context, though? So we got b0 is 20, but in the context, what does that mean? So what is $20 in this situation? It's the price you pay when? For what would cost you $20 in this situation? Yeah, so you're signing up for their plan, but you haven't rented any games. It's going to cost $20 to sign up, right? Before you even rent any games. $20 sign-up fee. Does that make sense? You're not going to get any games for that, but you're going to get the ability to rent games, right? So that's what it means. All right, so now B1 is the slope of this line, and we want to make a meaning out of that. So our slope formula, B1, is, you guys know what, we talked about delta, right, in this class? We've had that before? Yeah, so delta y is a change in this coordinate for the change in our x-coordinate. Okay, so we can take 2 points, say this is 0, 20, and say 10, 40. And we can calculate how much does the cost go up per number of games rented. That's what we're talking about. So how much did our cost go up for renting 10 games? So how much did the cost go up? 20, right? And if you've got hard numbers that you can't see that, you're going to do final minus initial, right? And that was for renting 10 games. So the slope is 2, right? So what does that 2 mean? So we found that for renting 20 games, it costs $10. Or say we said additional, right? So 10 additional dollars. You paid this $20 up front, but now you're going to pay an additional $10 to rent 20 games. And so then we got this number 2 for the slope. What does that number 2 mean? It's more than just the slope. It has meaning in terms of cost and number of games. For every 2 games you get, you pay $1. Agree with that? Other way around?
Changing Y is equivalent to a unit.
Okay, but $2 per 1 game. Yeah, so this is calculating a number. This is cost per number of games. So this is what this place is charging, $2 per game. So every additional game that you rent, you're gonna pay $2 more. So it's a rate, right? So a slope is a rate. In this case, dollars per game. What you will pay per game additionally for additional games rented. Okay, so I want you to so let's see. see if you can find the slope. Oh, and so therefore, then we can write the equation of this line, right? So we can say that y equals 20 plus 2x. And what does that represent? That represents every point on the line. So here, we've got the line-intercept and the slope. By using this equation, we can say, okay, what would my total cost be for renting 45 games? What would my total cost be for renting 45 games? What would you do? Okay, what did I say? 45 games? What was my example? Not enough? What was my example? 45 games? Is that what it said? Okay, what's the total cost for renting 45 games? What was that? How'd you get $110? Yeah, so by putting in 45 for x, it gives you the corresponding y. And so that gives you, what this does is it gives you every point on the line. So that's what's helpful about an equation of a line. It represents every single situation, every single point. Because there are not 1, 2, 3, 4, 5, there's not 6 points on this line. How many points are on this line? An infinite number of points. You see that? They've just highlighted 6 of them. But that line consists of many, many, many points. That's what that line consists of. It's just easier to draw it without lifting your pencil. But a more accurate way to draw that line would be to go like this. A bunch of points. That's a more accurate way because that's what it consists of. And this equation then gives us every one of those points. If you knew what the number of games rented was, you plug in the formula, it tells you the corresponding cost. Okay, so what I want you to do is, I want you to, I'll make this a little bigger here, the scale, but I want you to estimate the y-intercept, estimate the slope, write the equation, and then find the height of the grass at 6 days. Okay, this is on your green sheet. So everyone might have slightly different answers, but you're looking at the blue line. This is 0.02. We all should be in the ballpark of the same kind of answers. So what did I say? I said estimate y-intercept, B naught. And B1, write the equation. And then use the equation to predict grass height at 6 days. Go, you can work together. Okay, when you work on the sheet, please remember work this way, work up and down this way. Name and date, upper right-hand corner, you name and date. Work this way like a little sheet of paper. Don't work this way, or work this way. You can work together. Go, you have like a couple minutes. Oh, I got a 1b. 1b is to interpret these numbers in the context. Okay, so 1b is, once you get these two numbers, b0 and b1, interpret their meaning in this context about the grass. Okay, so 1a is, this is 1a. 1b, interpret. This is meters, okay? So this is days, and this is grass height in meters. Okay, I can come around and answer questions. You can work together. Don't forget 1b. There's a 1 part b over there to the left. The rate doesn't change, right? I could have picked these two here. Oh, they should be on the line. They need to be on the line. Yeah, you need to pick points on the line if you're going to get the equation of the line. Forget about the data points, right? You're just looking at the line. Yeah, so okay, show me what you're getting for B1. Did you get a value for B1? Here, there. Yeah. units on it. What does it mean? Grass height in meters. Grass height in meters. It's measuring the height of the grass after a certain number of days. Okay, just a couple more minutes. Finish this up. So this is three. This is three different in-class works coming back. If you have less than that, it means you missed class.
I just went to high school last year, so a lot of it I didn't figure that out.
Okay, I'll turn the rest back later. Okay. So what I want to do is interpret. So how did you interpret B naught? What did you say that B naught was in the context, the meaning? So yes, of course, it's the y-intercept, but what does it mean? Ashlyn, what did you say? The height of the grass, when? The original height, the starting height of the grass at 0 days, right? It's the height of the grass at 0 days. And then with the value you got for B1, what does it mean? What did you say that one means? Jason, what did you put for that? What's that? How much the grass grows per day, as he said. How much the grass grows per day. What do you think? Yeah, it's the rate, right? So that's what slope is. The slope is the rate of how much your y-dependent variable changes per unit of your independent variable. So yeah, how much the grass grows per day. Okay, are we good to move on? Okay, so then the point of this is, how did they get that line, right? So we took this data of the grass, and so we want to know, how do you get that line? Okay, so this just these examples just show that not all data fits a line. So just because we're focusing on lines now, just know in the real world, only some relationships between two quantities form a line. Okay, so which one of these would it be appropriate to use to find a best fit line? Which one of these, if we were saying 1, 2, 3, 4, 5, 6? 1, 2, 3, 4, 5, 6. Which one or ones of these would be appropriate to say, oh, we could talk about fitting a line to this data appropriately? People are saying 1 and 5. 1 and 5, exactly, okay? So 1 and 5 would be appropriate, but then these other, so we would want some kind of best fit curve. Same with this one, best fit curve. Don't know what's going on here, right? So who knows if there's a best fit anything here, okay? But yeah, 1 and 5, so something like this. Something like this. Oh, that's not a line. You get the picture. Okay, so given the data, how do we come up with the line that fits the best? So here's some data points. We got 4 data points, which is called a scatter plot. 1, 1, 1, 2, 2, 2, and 4, 6. So here's 2 possible lines that seem to fit the data. 0.5 plus 1.25x and negative 0.25 plus 1.5x. Okay? The way that we figure out what the best fit line is we look for each data point. We're looking at the error of the dependent variable between the point and then what the line predicts. Okay? So this error right here is negative 1 because the line is predicting 3. The point at 2 is actually 2. So that amount of error is negative 1. So what you do is you look at all those amounts of error. So you're going to have an amount of error for that point and for these 2 points. And you square that amount of error for each one. And then you sum up those squares. Okay? And then you want that to be the least number possible. So the sum of the squares of all the error of all the data points, the difference between what the line is predicting and what the actual data told us, the sum of the squares of those error values, those E values, is what we want to minimize. If we get the sum of the squares is the least, then this is how we say it's the best fit line. Okay, so this is the least squares criterion. It's the line that best fits a set of data points, the one having the smallest possible sum of squared errors. That's what I just said, right? The regression line is the line that best fits that set of data. And the equation is the equation of that line. Okay, so we're operating. There are other ways to find a best fit line. The one that we're gonna use is called the least squares criterion. So here's line A. So this y hat. Y hat then is what the line predicts, and y is the actual data value. So here are the actual output data values. And then this line, the y hat, is the value of y at those same x values. So the error is just the difference between predicted and actual. And then you have the squares, and then you add them up. And we did that for both lines. So according to the least squares criterion, which line is a better fit? Line A or line B? A or B? B is better because the sum of the squares is less of the error, right? The sum of the error, the squared error, is less. So let's look at those again. So according to the least squares, B does a better job mimicking the trend of the data than A does. Okay, does it make sense? Okay, here's another example. This is age and price for 11, how do you pronounce that? Orions? Orions. So here's this data here. So this is the scatter plot for the age and price data of Orion's age in years and the price. So, makes sense. Older car depreciates more. So this is a depreciation trend, right? The older the car is, the less it's worth. And so the price goes down. So using the least squares method, they came up with this equation. Y hat, so the predicted price for age X is 195.47 minus, and that's in hundreds of dollars, right, in hundreds, minus 20.26X. Okay, so I want you to interpret both, for your green sheet, interpret both those numbers. Write a sentence, explains what that number means and what that number means. What was the last number that I did on the previous, was it 4? On the previous set of questions I had for you? The 1, 2, 3, and 4? Just 3? So this will be number 4. Number 4, interpret the value 195.47. Again, that's in hundreds of dollars, right? These numbers would be all times 100. And then 20.26, again, remember the price is times 100. Okay, check with the person next to you. Make sure you're in agreement. Are we good to go? Feel confident about what you wrote? Okay, so use of a regression equation to make predictions outside of the data area is called extrapolation. It's called extrapolation. So the data is all around 4 to 7 years. If you use the line then to predict beyond 7 years or before 2 years, it's called extrapolation. So if we were to say, oh, then after 8 years, it looks like the car price will be about, I don't know, 3,500? 3,000, 3,500, then we're extrapolating. We're extrapolating because we're predicting values outside of our data range. No, that's it's just there's a lower level of certainty, right? So if we were making a prediction within here, we'd be more certain about our prediction than outside of the data range. Okay. So maybe if we took more data, what we'd see is we'd see lots of points like this, right? Over here. And so now your extrapolation isn't accurate. But maybe we would see data like this. But if we're going with a line, this is what a line predicts. Okay, so this one out here is called an influential observation. Why? Because if you remove just that one data point, you get a significantly different best fit line. So if we were to find the best fit line with all the data points, we get the one that you guys interpreted. Remove just that one data point, and it's a very different result. So because of that, that one is called an influential observation. Okay, along with that is the idea of an outlier. Okay, so an outlier is a data point that, for whatever reason, we want to remove it from the data set. So we may or may not want to, this particular, an influential observation, we may want to remove it, or we want to take more data to see what's really happening. An outlier is something that we want to remove, for sure. So it's not that these are two different things. You can have outliers that are influential. You can have outliers that are not influential. You can have influential that are outliers. You can have influential observations that are not outliers. But an outlier might be something like from recording error, from an error in recording. Okay, for example, that's an example of why you get an outlier. There was a mistake. They wrote the data down. They were taking the data, and they wrote something down wrong. And so you get a point like this. Right, so they wrote 230 instead of 2130. So that maybe the real data point was supposed to be 2130, and they wrote it down as 230. And so this is in our data set. That's an outlier. So an example is when they make a mistake of getting an outlier. Okay, do those terms make sense? Influential observation and outlier. Okay, so let's look at some examples of, so we're going to let StatCrunch, and actually getting that best fit line is a complicated process that we're going to let StatCrunch do for us. So we want to focus on interpreting and using and really understanding what it is. But actually that, because if you think about it, it's like we're considering all possible lines and then picking the one that has the least sum of the errors, right? And so that's not something that comes mathematically easily. So these are some of the equations that are involved in finding that line, okay? Okay, so for that reason, we're going to let StatCrunch do the heavy lifting for us, and we want to be good managers, right? We want to know what the numbers mean, interpret, and use the results. Okay. So let's look at some examples here. Here we go. $49, $52, $71. Someone write, we write that down? 49, 52, and 71. Thank you. Okay, so here's some data. X 32541 and Y, corresponding Y is 42970. And so we want to find the regression equation. Okay, again, to get that best fit line based on the least sum of the squares of the errors. Complicated mathematical process. We can let the technology do it for us. So we're gonna hit our stat crunch icon, and that data comes up in stat crunch as a X column and a Y column. We're gonna go to stat. We want regression. Stat, regression, simple linear. Okay, so you want to select your independent or explanatory or predictor variable and it's going to be by column name, right? So when you do it in your homework, the columns may come up with actual names of the quantities, and then those names will show up here in these menus. So in this case, we want X to be X, we want Y to be Y. Okay, and then we don't care about a hypothesis test, but you can't uncheck it, so just leave it. We don't want a transformation. We want a fitted line plot. Okay, so that's all you really need to do. You need to set your X variable column, your Y variable column, and then make sure fitted line plot is saved. And that's what you need. And then we're going to compute. And then there's lots of information here, but the one we're interested in is this. The best fit line. Based on the least squares criterion. So it gives us the y-intercept and the slope in the form, in the equation form. So negative 2.5 plus 2.3x. So negative 2.5 plus 2.3x. Okay, so now you want to graph the points and then pick the one that's an accurate representation of the graph. If you want a bigger version of any graph, you just click on this little icon here and it gives you a larger version. So we can just do it ourselves here quick. So 1, 2, 3, 4, 5, 2, 4, 6, 8, 10. And so we got 3, 4, 2, 2, 5, 9, 1, 0. That should be enough for us to find the right one. So which one is right? Looks like D is the one that we want. So you can plot the points enough to see that D is the right graph. Okay, so there's an example without application. What was the next one in the list there? 52. Okay. Following are the chest size and weight of 6 randomly selected bears. I don't know where they get this stuff. All right. Here, X denotes the chest size in inches, and Y denotes the weight in pounds. Use the information to complete parts A through F. So again, Y hat is our predicted relationship between these two variables as a linear equation. So we're going to open up in StatCrunch. And so we got chest size in inches and weight in, is it pounds? So we're going to do stat, regression, simple linear, x variable came up as x, y variable y, and then we want to make sure we're doing a fitted line plot. There it is. Okay, so let's do another interpret. Remember, x was the chest size in inches of the bears, and y was the weight of the bear in pounds. Okay, so chest size, weight of the bear in pounds. Let's interpret. So is this number 5 on your sheet? Is that right? Is that right? In this context, you're talking about the bears. When you're talking about these numbers, you're talking about how it relates to the bears. This is chest size in inches. And this is weight, pounds. Those are kind of small bears, aren't they? Only 200 or 300 pounds. Aren't bears like big? Okay, anyway. Go. So write out a sentence for each of B0 and B1 for this particular situation. So when you do B0, you have to keep in mind it's kind of a hypothetical. It's not realistic, right? So when you're interpreting that, it's not a real situation. That's your hint. Okay, it's not a real situation, but it's kind of a if this were possible, this is what it would be. Okay. Are we good, or do you want to talk about it with your neighbor? Yes, sir.
How did you get that in stat?
Stat. I'll do one. We're going to do another one. Yeah. So here's your chance to talk about it. If you want to talk about it, I'm going to put the answer in to the. Oh. Oh, 2. So it'll be 2, 3. Ah, thank you. Okay, and then we could plot these points and see which one. So first of all, we can just eliminate some right off the bat. What happens when chest size goes up? Does the weight go up, down, or stay the same? Up. Okay, so that immediately eliminates A and D. So it's one of these two. So we can just pick one up and see. This is about 37. Do we have a? We don't even have a data point at 37. 40. Oh no. What? Okay, this scale is whack because this is like these are 6 each. 6, 12, 18. Yeah, so this is 6. Is there something right around 40 and 256? Yeah, the scale is. So you have to. It's one of these two. You can figure it out, right? You're gonna make your own plot and then compare it to the one that you have. So I'll just try this one. Okay, lucky guess. Okay, but it was gonna. We knew it was B or C. Just have to make our plot and see which one matches. Okay, let's keep going. Describe the apparent relationship between two variables. Weight remains constant as chest size increases. Weight tends to decrease. Weight tends to increase. There is no apparent relationship. A, B, C, or D? C. Identify the predictor and response variables. Let's not read the answers. Let's just say, what is the predictor variable? What is the predictor variable? Chest size is the predictor. That's our independent, or X. Response is weight. So predictor is chest size, response is weight. See? Outliers, potential influential observations. So let's look at the graph for the correct graph. What do you think? Any outliers? No outliers. Any there that you think if we took it away it would significantly change the line? No. They're all really close to the line, right? So taking one away isn't going to have a big effect on the resulting line. So I'd say none of each. Okay, and now it says it wants us to predict the value of the response variable for a 50-inch chest size for your sheet. What's that, number 6? Are we on number 6? So use our best fit line to determine what would the value of the response variable be for 50-inch chest size, and let's interpret your number with a sentence. So you're going to get a number. What does that number mean? What does that number mean? Sure. $56.23 plus 4.81x. 56.23 plus 4.81x. And it says, find the value of the response variable for 50-inch chest size. Okay, check your work with the person next to you. Make sure you got it right. What was the last one? 71? Daniel, what was the last one? 71? Okay, one more example. Okay, so this is per capita income and per capita alcohol consumption in 6 different countries. So X is income in thousands of dollars. Y denotes alcohol consumed in gallons per year. So thousands of dollars of income and alcohol consumed in gallons per year. So graph the data points. We do that fast? Let's do that fast together. Let's graph these data points. So it like 10, 20, 30. And same thing. 10, 20, 30. Okay, so about 20 and 20. I'm just gonna, just enough so we can get the answer right, okay? 23 and 30. 27 and 28. 20 and 16. 28 and 20. And 24 and 31. Is there one of those that looks like that? This one maybe? My rough sketch is too rough. I guess it must be this one. Okay. Decide whether finding a regression line for the data is reasonable. So there is a linear pattern, there is a clear nonlinear pattern, there is no pattern. So linear pattern, nonlinear, or none. So let's actually blow that up. This is what it was, right? Linear, nonlinear, or none? Nonlinear, okay? So this is looking like from the data we have that it's curved, cupped down, right? Cupped down. Okay? Doesn't mean not reasonable, right? So it's asking what's the regression line, but a regression line is not reasonable because we said it's nonlinear. Potential outliers or influential observations. Well, that would be, it's kind of a weird question if we're already saying it's nonlinear. So let's see what our choices are, okay? So let's see what our choices are. See what answer makes the most sense. No outliers or influential observations, one or more. Not applicable since the regression line is not reasonable. So outliers and influential observations are in the context of having a linear trend. Okay, any questions?